Thanks very much, Michael. Thanks everybody for coming this morning. Today's lecture is Reflecting on Planning Models, a Challenge for Verification and Validation of Planning Systems. So here's a brief outline. So what we're going to talk about is a form of model-based planning for cyber-physical systems, as opposed to other kinds of planning and scheduling applications, which is suitable to the ICAPS Planning and Robotics Summer School. And what I'm going to talk about is a problem that NASA explored a couple of years ago, which is that when we build model-based planners for these kinds of systems, be they spacecraft, robots, whatever, there's a gap in abstraction between the sort of lowest level command and data representation of these systems and the more abstract model-based systems that we all know and love in the planning world. And it occurred to me that what we do is we fail to document this abstraction that exists between these two levels, and that if we did that we could get some advantage out of it, but there's some problems that remain in the validation, the verification and validation of model-based planning systems. So we're going to talk about what these abstractions look like, how to document them, some of the things one can do when one documents them, and some of the remaining challenges at the end. Okay, so for our motivating example, because I come from NASA, our cyber-physical system example will be a spacecraft. And so we'll start with that. So suppose we have a spacecraft like the one that's in the lower right corner. It's a very cute little spacecraft. We'll talk more about it later. And we want to develop a mission planning system for this spacecraft. Most spacecraft are robots. Some of them are very large robots that people live inside. But most of them can be thought of as robots. And the mission planning system that we would like to build is one that could either be part of a ground system, so it could be something that mission planners use. Alternately, it could be part of an autonomous spacecraft, and for our purposes, it really doesn't make any difference, because the interesting challenge, does everybody have your Zoom bingo cards out? We're going to get to Zoom bingo before the end of this talk?
Sorry, I was muted. There's another one for everybody. Yes.
Okay. All right. So the running example that we'll use through this talk is that we want to model a change of orientation or attitude of the spacecraft, and we're going to talk about how we would do that. And we'll use some NASA jargon here, so you all can be totally cool with your friends. Changing the pointing attitude of the spacecraft is referred to as a slew. So in order to talk about changing position or orientation, we obviously need some sort of coordinate system, probably very familiar to you all in robots. We need to choose that coordinate system. What it is not terribly important. Let's assume in this case that it's Earth-centric. And like many other motion operations, we need to think about what constrains a slew. And for spacecraft, there are a lot of different kinds of constraints that we need to think about. So one common one is we need to think about power, and in particular solar panels. So the spacecraft that I have below has solar panels all over it, and so you would think it's not constrained by solar generation. But if you have a solar array wing and the wing is only able to point in one place, then you have to ask yourself, how is power generation going to constrain this? How much energy am I going to use when I do the slew? What kinds of spacecraft modes do I want to fix or change before I perform this operation? Am I going to lose communication while I'm slewing? That'd be bad, and so on and so forth. So there are all these different kinds of constraints, and they all need to be documented. So what we're going to do is we're going to walk through the kinds of things that you need to do in order to slew your spacecraft. And we'll start with the low-level command and data representation. And the color coding on each of these facets of the spacecraft, these subsystems, these types of constraints, this is important because we'll use these later. And so we'll walk through these one by one. So a common way that spacecraft know where they are is using a star tracker. And so the star tracker takes pictures of the star field, and it uses that plus a model of where the star field is supposed to be in order to localize. But while you're slewing, that may not be terribly useful, so you may want to turn the star tracker off while you're slewing. So there's a command to turn the star tracker on and off. You might also want to toggle the CPU. You might want to, because the CPU burns a lot of energy. And so there are commands to turn the CPU on and off. There are commands to start and stop various processes that increase CPU utilization. Some of those processes are things you need in order to do things like slew the spacecraft. There can often be a power distribution mode. So if I have spacecraft solar arrays and batteries, if the solar arrays aren't generating energy, you need to draw energy from the batteries. If the spacecraft is in the sun, I want to recharge the solar arrays and so on and so forth. Let's talk a little about reaction wheels. So reaction wheels are basically spinning disks, and the way that you change orientation is you spin these disks up, and it's a momentum transfer operation in order to change where the spacecraft is pointing. So you may have many reaction wheels, for example, 4. And what you can do is command these reaction wheels to rotate at a certain velocity in a certain direction, clockwise or counterclockwise. And that's the way that you actually do your slew, right? And at the very bottom here, we have the battery. And the state of the battery is a function of how much solar energy is coming into my 2 solar arrays. In this case, I'm pretending I only have 2, and what the battery's state of charge is. So that's my command representation, okay? Now, there's also a lot of data associated with all of these subsystems. So for your orientation or position, as determined by your star tracker, you may want your absolute XYZ coordinates, and you may want your rate of change of your XYZ coordinates, and you may also want to know if the solar array is on or off. It'd certainly be very peculiar, for example, if you were getting position and orientation or information from a star tracker that was turned off. That would be an indicator of something wrong. And we'll talk about faults a little bit at the very end. For the CPU, we want to know whether it's on or off and what its utilization is. For power distribution, we want to know the power distribution mode. Are we drawing from solar arrays or the battery? We want to know what the battery's state of charge is, and we want to know what the reaction wheel rate of rotation and rate of change of rotation is, and we can use a negative sign to indicate whether we're going clockwise or counterclockwise. Okay, so this is a whole heck lot of information about our little spacecraft here. And by the way, this is a very little spacecraft, as we will see. We haven't even started talking about how to build an action to plan the slew. So hopefully you're starting to get the idea that this abstraction problem that we're talking about is a fairly serious one, if you already haven't decided that it is. So I am hopeful that most of you have seen PDDL style model-based planning before, and if you haven't, this is a fairly brief introduction. There are people much better suited to speak to this than me, but these planning models that we in the AI world are accustomed to thinking about, we build models, and the models consist of things in the world, which we refer to as objects, although they may not be real objects. Predicates that describe properties of things. For example, a robot can be at a location, a spacecraft can be pointed at a position in the sky, and that proposition is true or false. Sometimes that's not rich enough and we need to have functions that describe numerical properties of things, for example, the state of charge of our battery. Actions are ways of changing the properties of things. And a planning problem consists of one of these models, an initial state description, I am pointed at the moon, and a set of goal states, I would like to be pointed at the Earth. And I would like not to have drained the battery, and I'd like a functioning communication system, and so on and so forth. So the planner's job is to read this model, read the initial states, and either produce a plan or prove that no such plan exists. So what would our spacecraft slew look like if we tried to think about it as one of these model-based planning types of descriptions, as opposed to this much more low-level description that I described to you? So what we have here is the same picture of our spacecraft and the same color coding of our major spacecraft systems or features. But what I've now done is represented a bunch of propositions and one function, which is the state of charge of the battery. So if I were an expert at modeling in PDDL 2.1, which is the simplest temporal planning representation that's very commonly used in AI, I might write a model to slew our spacecraft, and it would look something like this. So again, remember those colors. So the first thing we have is we have the name of our action. We then have a set of objects that are parameters to this action, and our object in this case are abstract objects. We are using pointing positions in the sky of things that we are interested in as our objects. We then have a set of conditions under which this action is going to work. And the conditions say things like you have to be pointed at the place that you were initially pointing. The CPU of the spacecraft must be turned on throughout the entire duration of the action. That's what that at start and overall qualifiers are for, and so on and so forth. And then we have a set of effects. And the effects are that we're going to reduce the total state of charge of the battery by some amount. We are going to be slewing throughout the entire duration of the action, and at the end, we're not slewing anymore, and so on and so forth. Here is a pictorial representation of what the action looks like. Here is our initial state. As I said, we're pointing at the moon. The CPU is turned on and guaranteed to be turned on for some extended period of time. We are initially generating, we're not slewing, and the battery state of charge, you can see there's this orange-yellow line here, indicates that we have 4 units of energy, whatever units we're measuring, BTUs, whatever. Amp hours is the usual thing that we talk about for batteries. So let's now insert our action, which is slew from the moon to the Earth. And when we do that, we see that there's this progression of changes. We transition through slewing to not slewing. We transition through a period of time where we don't know what we're pointing at to a period where we're pointing at the Earth. We stop generating and we fail to generate through it thereafter. And the battery state of charge goes down by 2 and life is good. Now, those of you who are PDDL purists will note that I'm using a more SAS-like representation rather than proposition true-false values. It's more natural to me, just deal with it. If you have questions about what this means and why it's interesting, we can take that up later. That's a joke. You are allowed to laugh. Okay, now suppose that we had a slightly different initial state where the CPU was not turned on. It was guaranteed to be turned off for some reason, just when we wanted to put this slew operation in. Well, then we can't do that, and the action doesn't work. All right. Okay, so that's the end of the table setting, as it were. Now we're going to get into the fun stuff. Okay, so the contentious proposition is that these planning models, these abstract models of robots and spacecraft, we must abstract, and I hope that that's very clear from the 2 different levels of representation that I've provided. And so there are a couple questions that sometimes come up at this point. The first one is that, well, how do you do that? Why don't you document them in the first place, and what can you get out of it? And so that's what the rest of the talk is going to be about. Okay, so we're going to talk about 2, or if you like, 3 slightly different forms of abstraction. So predicate and function abstractions map the lower level data representation of either the spacecraft or the robot into either predicates that are true or false, or functions that describe numerical states at a higher level of abstraction. And we need 1 level of abstraction per either predicate that we want in our higher level model or function. The second form of abstraction is, I call it a command refinement, because really what it is, it's a function that maps a planning action to a command sequence. So it's sort of easier to talk about it that way. And again, each action has one command refinement, and we'll talk some more about what each of these look like in some more detail. So here's our very familiar picture. We aren't going to talk about all the predicate abstractions that we need, but we'll talk about a few of them. So before we get into the first one, I just want to point out that the Earth, the pointing attitude Earth, has some XYZ coordinate system, right? And it's got a fixed set of XYZ coordinates. So the pointing abstraction, pointing at the Earth, what we can do is say something like this. We're pointing at the Earth if the X position is within epsilon of the Earth's X position, the Y position is within epsilon of the Earth's Y position, and the Z position is within epsilon of the Earth's Z position. So that's a pretty straightforward thing. You see this come up in robots, in spacecraft, in UAVs. It's basically protecting yourself against, imprecisions in your measurements, imprecisions in where you think this thing actually is located. because if you used an exact point, then you would never actually be where you wanted to be, and your robot would sit and spin forever, which would be a bad thing, especially if you paid several $billion in order to put it into space. So that's one example of an abstraction. The generating abstraction is a little bit more tricky because here, what we would like to capture is a couple of different things. We want to capture the power distribution mode. So we want to guarantee that we're distributing power from the solar arrays. We also want to guarantee that the total energy that is being distributed from the solar arrays is greater than some value. And we also want to guarantee that the battery actually is getting juice in it. So all three of those things need to be true in order for the proposition generating to hold. And then the last one, total energy consumption, this is a function abstraction. And suppose there are three different consumers of energy because we've turned on three major subsystems of the spacecraft. And suppose that we want to claim that we're using 2 units of juice. Well, basically the sum of those three things has to equal 2, right? And you could even put a plus minus epsilon there to protect yourself. Okay, so those are the kinds of predicate abstractions that we can and must write down. So now I have a command refinement, and this is the command refinement for our slew operation. And what the heck is going on here? What is all this stuff? Well, you remember at the very beginning, we had all these different commands that we could send to all our different subsystems, right? Well, so an actual slew operation turns out to be a fairly complex thing. The first thing you want to do in this is you want to turn the star tracker off. You want to change the power distribution mode to run off the batteries, not the solar arrays, right? Because you may not want to rely on solar energy. You want to do some things to the attitude control system mode. You want to stop a process. You want to start another process, and then you want to spin up the reaction wheels, and you want to spin them for a certain amount of time and in a certain direction, and you don't want to spin them all at once. And the numbers in brackets here are absolute times. So, so the point that I want to make here is not that this is an actual command script for changing the slew, because if it was, I couldn't show you anyway. But these are the classes of things that happen, and there are a lot of them, and they're very complex, and all of them need to be abstracted in order to construct this action. And so from this, we're getting both the duration and we're getting all the preconditions and effects, and they all have to come from these lower level commands, right? And so I'm just walking through all of this stuff again. Okay, and so somewhere someone has written down this script or set of scripts, or this is the way that the spacecraft's flight software or the robot software behaves. And we kind of know that, and we kind of know that we do this documentation thing, but we never do it formally. And so what I'll now do is talk about how the formal declaration of all of these things can get you to the detection of errors in your model, if not actually how to fix them, which is the challenge part. So you all have homework, or at least you will by the time this talk is done. Okay, so modeling is error prone, and having to document these abstractions just compounds the kinds of things that can go wrong, because now we can have problems in the abstractions as well as in the model. And it's also very obvious, it should be anyone who's used real hardware, that the models become wrong over time for all kinds of reasons. The system itself can change, it can degrade, you can move into a different operating environment that changes the way that the system behaves. You may want to use the system differently than you did before. The goals can change, the objectives can change. You may want to use different modeling paradigms and so on and so forth. So being able to detect these models, not only upfront as you're building them, but also in the presence of model drift, these things are all important. So here are a long list of the kinds of errors. So planned domain modeling errors at the bottom, we're all very familiar with those. Raise your hand if you've never committed a modeling error in your life. So I'd like to go out for a drink with you and find out your secret. But in the presence of abstractions, we have a lot of different fun things that can go wrong. So we can be missing a command in our command script. The commands could be issued in a bad order. Parameters to the commands could be incorrect. So we have the right thing at the right time, but we gave it the wrong parameter. We can have things at the wrong time, or in the abstraction step, we can be either missing an abstraction or there can be some sort of mistake in the abstraction. So we might think we had the wrong parameter, but in fact, we had the right parameter and we thought we had a different one and we did the abstraction wrong. Now, the problem is those are the things that can go wrong, but the symptoms are quite different, unfortunately. And there's too much indirection between the symptoms and the actual errors. So let's talk about what some of the symptoms look like. So first and foremost, we might have an action in a plan that when we try and simulate it, it just didn't go. Now, there could be a lot of reasons why it didn't go. So one possibility is that there's a condition missing. So we thought that we had established the condition by dint of something else in the plan, but it just didn't happen. Another possibility is that the action executes, but it didn't have an effect that we expected. There could be some extra effect, something that we didn't anticipate happening, and it happened anyway. And we're like, what happened there? One possibility is that actions can execute when we didn't expect them to. So there's some deficiency in the state in which this action is executing, which we would expect would lead the action to fail, but it worked anyway. What happened there? So obviously we're missing something. If you have instances of an action that execute and other instances that don't, that's an indicator that there's some condition that you need that you don't understand. And then of course there can be various timing discrepancies, action duration discrepancies, and predicate duration discrepancies. So we'll see a couple of pictorial examples of all of these. So here's our slew action as planned, but suppose that pointing at the Earth doesn't start when we think it's supposed to start. It doesn't start right at the end. There's some delay. What happened there? Well, one possible thing that could happen is that we establish a very tight error on our pointing tolerance, and it just takes the spacecraft a lot longer to establish that it's pointing at the Earth than we anticipated. So that could be the explanation for what happened there. So here's an example. What happens if, we didn't think we were supposed to be generating after the slew is done, and all of a sudden we see that we are generating and that battery state of charge is going up again? Well, what happened there? There's an unmodeled effect. Well, so what happened there is that we made a mistake, and in the command script, we changed the battery distribution mode, and we're stably pointing at the sun and generating energy, but I just forgot to put it in the model. So that's the thing we'd like to be able to detect. Okay, so with those couple of examples of what we want, how do we get it? How do we get it? So we start off with our model and a planner. And this model produces plans, and inside that plan are a whole bunch of actions that are going to do what we want. Well, the next step, with the command refinements, we can take those actions and we can produce a set of actual commands at specific times. We'll talk more about specific times in a moment. And we can send these commands in some initial state through either the spacecraft or a simulator. And the output of that simulator or the real spacecraft is data that describes what all the major subsystems are doing. And from this data, we then take all the predicate and function abstractions. And now what we can do is produce the quote unquote actual states in the planner's language that were experienced during the execution of this plan. And now we can take what the planner thought was supposed to happen, and we can take what actually happened, and we can compare them, and we can then generate a very large list, hopefully a very small list, hopefully an empty list of errors, all those errors that we just talked about. After that, we then fix them magically by some process that does not exist, and then we try again. And we can keep going around this loop over and over and over again until we run out of money or until the planner works. Hopefully we get the planner working before we run out of money. All right, so that's the vision. How do we get that vision? How do we make that vision a reality? So when we write these function abstractions or predicate abstractions, we're doing a couple of things, and there's a lot of words here, but the story is actually quite simple. The first thing that we could do is we could take the value of some data item at this low level of abstraction and we can make it smaller, right? We're just doing a cardinality reduction on the domain. And there are some special cases. We can eliminate elements of a discrete domain. we can map reals to integers, integers to positive integers, and so on and so forth, right? There are a lot of examples. Shouldn't be very mystical. The other thing that we can do is we can change the number of variables. We can take primitive variables and we can either combine them or just get rid of them. The caveat here is that we do need to make sure that the total cardinality of this set of variables is also reduced. So we can't drop a variable and then increase its domain to an infinite domain. That would be bad. That's not the point. The point is to make things smaller. So what I'm going to do now is walk through a variety of algorithms. One of my 440 coworkers is joining me to walk through the algorithms here. So what these algorithms are going to do is each of these algorithms is designed to catch one of the kinds of errors that we talked about. And I have some notation to describe how these algorithms work. So there are n actions in our plan. There are a total of p sub n action conditions in effect for each action n. This is basically just the size of the action description. As predicate types in the model, there's one abstraction per predicate or function, as I said. And I should have put numerical functions in there too, I forgot. And then there are m sub p predicate instances in a plan. We have the number of commands in each command refinement, the total number of data items in the subsystem. This is at the robot level. And then the number of time ticks over which the data is going to be recorded. And so, oh yeah, you can do the same thing for the numbers. So pictorially, what's going to happen is this. So when this simulation is done, after you've taken your command refinements and run this thing through the system, what you have, as I said, is you have t data items. And you have recorded these t data items regularly over r time ticks. And then you have these abstractions, and they're s abstractions. So at the first step, what you do is you basically, for each time tick, you run all your abstractions and you produce for each time tick whether a proposition or a numerical function state in your model held and what its value was. And that takes t times r times s, t data items, r time ticks, s abstractions. And then what you do is another pass where you group things into temporally extended predicates or temporally extended numerical function values. And that is the first pass, after which now you have the data representation of the plan. And you have the data representation of the run in basically the same language, in the planner's language. And that's basically what all of this text says. So that's very boring compared to the picture, and it's just not that difficult. So what happens next is the fun part where you actually get to compare what the plan said and what happened at execution time and see what kinds of problems you come up with. And we would like to distinguish between cases where an action doesn't work versus cases of timing discrepancies, because timing discrepancies, as we'll see, are somewhat more common, and they arise for a number of reasons that might get one less excited, perhaps, than an action failure or an unpredictable or unpredicted action behavior. So we are assuming that our plans are not temporally flexible. And I think that this assumption can be relaxed eventually, but it just makes the explanations a little bit simpler. The command scripts are usually fixed time scripts or time tag scripts, as people often like to say in the spacecraft world. Sometimes you might imagine that you're triggering something more interesting, like a VML state machine or a FlexB state machine, or something like Plexel, which has more complex behaviors. And that just makes the analysis harder, but we're not going to talk about that today. And so one of the consequences of this fixed time plus simple command scripting is that either actions start on time or they're not executed at all, right? So there's no shifting of action times. They can end early or late, and predicates can happen all over the place, as we'll see. But that makes it nice to check what happens with actions. So the other thing that lets us do is record exactly when an action starts, when it ends, or whether it was supposed to start on time or not. This is akin to a happening predicate in TL plan or TAL plan, if you know what that means. And so now let's move on. Okay, so the first thing we'll talk about is detecting action failure. So as we said before, this is manifested by all those things that you thought were going to change, they're not going to change at all, and you have some indicator at time 12:10 that the action didn't work. So this is very easy because we know we have something in the executed plan that indicates what happens with each action. It's very straightforward to check those. It's order n, order number of actions. Now, if the thing that didn't work was because of some missing condition, something like this, now what we need to do is, for that action that's missing, we may need to take a look at its conditions and do some groveling around in the predicate representation of the executed plan to figure out what happened. So in the worst case, we have all kinds of action failures. So there could be order n action failures. And we have to look at something approaching the size of the model. So that's just, you know, the sum over the action description size of all of the actions. So again, that's fairly straightforward. So if an action occurs, but there's some missing effect, like we're not pointing at the Earth after we finish our slew, which would be a very sad thing, especially if we were communicating evidence of aliens on Mars, that'd be bad. Again, it's very similar. We now have to look at the effects of every action. We have to compare the effect propositions to the propositions that are in the model. Again, it's pretty straightforward, just sum over the action sizes. So if there's a duration discrepancy, action takes longer or shorter than anticipated. Again, quite straightforward. All you need to do is check every action instance and say, hey, when was this thing supposed to end? Did it end on time? Much the same story for timing discrepancies of established propositions or established numerical function values, except now we have to look at all the instances of all of the predicates in the final plan. There is a subtlety about this that we'll talk about a bit at the end. So how could it be that an action executes with fewer than expected conditions? At the initial state, right, the initial state is going to be identical to the planner, unless you made some sort of error. But some action could have failed or could have failed to produce an effect, setting up the opportunity for some action later in the plan to execute in a context that you didn't anticipate. And so it could be, it could come up. And again, you know, it's pretty straightforward to check this. You now want to take a slightly different look at what it is that has happened. So for an action that executes, you don't want to just assume that all of its conditions held. You want to ask, hey, did this thing execute when fewer conditions than I expected hold? And again, it's just, you know, sum of the action sizes. Not very difficult. So the case of an action that has more conditions than you anticipated required is a little bit more strange. How does this come up? Why did this fail, right? So there's a bit of description about how I imagine that this could come up. So in order to figure this out, you need a case where the action fails sometimes and doesn't fail other times. It succeeds sometimes. And in both of these cases, all the conditions that you anticipate do hold, but there's some difference in the extra states, right? What's true in the case where the action executed successfully that was not true in the case where the action didn't execute? So there's a horrible n squared here. We've never seen that before. That's ugly. But this is sort of a perverse case. It probably doesn't come up too often. And the point is that, you know, you could just assume that the same action is executing and half the time it works and half the time it doesn't. And then you can sort of compare the cases. This is a massive overestimate, so I don't anticipate that this will come up very often. Unmodeled effects. So this is we forgot to put generating into the model case. And again, you know, it's a pretty straightforward thing. But now you have to, for each action, look at all the things that weren't supposed to change and see if they did. And so again, that's just the number of actions times the total number of predicate instances in the model in the worst case. Not a big deal. Okay, so there are a couple of technical things that I've sort of swept under the covers here. And the first and foremost one is the isomorphism problem. If there are lots of different occurrences of a ground instance of a predicate in a plan, then timing discrepancies between planned and occurred propositions in the model can look a little silly because basically you're confused about which instance of a proposition that you're looking for. But the trouble is, at execution time, you can't guarantee that things are going to go exactly where they're supposed to. And so you can use a heuristic, which is just report the discrepancies of the quote unquote closest pair or some subset of pairs of the same predicate, and you can ignore the rest of them. And chances are pretty good that if you find a problem with those, that it's a real problem, and you can probably ignore the rest. This is not required for actions under the no flexible duration assumption, because we know exactly when actions are supposed to occur. So we know how to check the timing discrepancies of ground instances of the actions because we know when they start, right? They're going to start at the same time. So that's not a big deal. All right, well, so we've put all this machinery together. What the heck do we get out of this? Well, so we have all this evidence now that something has gone wrong, but one action can have a lot of different problems. And the evidence is sort of indirectly pointing at something that has gone wrong, but it's not a direct path to fixing what went wrong. The model could be wrong, the abstraction could be wrong, there could be both. And we don't really have, aside from human expertise and effort, a way to get from this list of problems to the fixes to the problems, but it's a lot more than you have if you don't have the documented abstractions, because you can now see that you can just construct and run a bunch of these automated tests in order to start figuring out whether you have an issue in the first place. So I want to talk very briefly here about how language semantics can sometimes cause more problems of this type in these domains than we would like to see. And if we looked at that command abstraction for the slew, we see that it's very complex. There's lots of intermediate timing that we're all sweeping under the rug with the abstract slew action. And so effects and preconditions really are occurring all throughout this very long action. And PDDL 2.1 can only represent conditions at the start and the end, and effects as well. There are languages that are more expressive where you can express things sort of in the middle, and that would make things simpler. But if you are using one of these simpler languages, and there are good reasons to use those simpler languages, it's not an implicit critique of any language in particular, but what can you do about all of these quote unquote false alarms for timing discrepancies that you're going to get out of this? Well, you can modify the timing check, which compensates for some of those limitations, but it introduces complexity in the timing check, and it's not clear that that's the best answer. So I really want to point this out just as an example of some of the kinds of bad things that can happen. So here's our slew action command sequence, and here's sort of an exploded view of our abstract slew action. And you can see that all kinds of things are sort of happening in the middle. The change of pointing mode and the change of power distribution configurations are happening earlier, but the reaction wheel changes are happening somewhat later. And so this stuff is not all lining up with the exact beginning of the action at all, and things are happening in intermediate times. And some of this stuff, it's going to happen because of the abstraction, because of the language semantics and the language features that you're using. And you'd like to be able to easily suppress these things or get them as warnings or something like that. So that's the point. Okay, we're almost done. Because the correcting models part is short because we don't know how to do it yet. Okay, so we talked a little bit about the reasons why things are going to change throughout at the very beginning, so I'm not going to spend a whole lot of time on that. There are numerous advantages that we can imagine to having this kind of validation technology online, not just upfront. It would be very nice to imagine that we could take advantage of all the data that's on board the spacecraft that we can't send back to ground. That data is often available at a higher data rate. We can sort of do this evaluation all the time and try not to pay the cost of communication. The challenges of this are that spacecraft processors are very small, they're very crippled, they're very slow. Using the processor is very energy intensive. So it isn't totally clear that you get all the benefits that you might imagine here, but it's something to entertain for the future. So one possibility is to collect a bunch of data on when actions work and don't work and when there are timing discrepancies, and just use a classifier in order to try and get a better handle on exactly what conditions are causing this problem. So you can imagine this is an action that's under development. and it's just not working right, and we're not quite sure why. It's got these very complex command scripts. And so this is a possible route forward. Another possibility is that you use clustering instead of classification. And what I've got here on the bottom is a cluster of a combination of slew rate and sort of arc distance of the slew with 3 possible outcomes. One possibility is that in the middle, in the green, the slew does what we want it to. In the red, on the outside, it doesn't do what we want it to. And in the middle, sometimes it works and sometimes it doesn't. And this idea actually goes all the way back to a nice paper by Dave Smith in the aviation domain, and he was doing this with airplanes, but you could imagine doing the same thing here. What you want to do is ask yourself, hey, for those yellow points where the action sometimes works and doesn't work, or I'm not sure it's going to work, can I judiciously act in that space to try and do model refinement, right? Can I run a test there and gather some more information and try and figure out exactly how this action is supposed to behave? So that's an intriguing idea. Faults. Let's talk a little about faults. So faults are very, very important in human spaceflight and robotic spaceflight. It's a special class of system degradation or an unexpected event. But now, instead of using data and or machine learning in order to characterize what is happening, we have an oracle of sorts, and that's the fault management system. The fault management system can tell us some things about what the problems are and what the consequences of the problem is, and we can imagine using that to directly change the planning model rather than having to do a bunch of experimentation. And just to schematically put that into context here, there's now this fault detection system, and the fault detection system is directly informing the model rather than going through this validation loop. So that's a promising idea. It's a lot harder than it looks, as I have found to my sorrow. And alas, we're not going to talk about it too much more here, except for this cool picture where we say, hey, suppose that one of our reaction wheels is degraded and it's not working as well as it used to. And so we might be able to directly update how long it takes to do slews because we have to use this reaction wheel and so on and so forth. So we would just be able to change the duration and move on. All right. So I think I've mostly said a lot of these things in one form or another already. The space of abstractions is very large, especially when we're dealing with continuous domains, and that makes things challenging. Algorithms are resource intensive, software has mass. That isn't a joke. Unfortunately, it's very sad. It's true. And we just don't really have a good handle on how to solve these kinds of problems. Clearly, one would be very suspicious of doing experimentation during the execution of a real mission. So that's also a problem. Let's see. So this is a bunch of fun stuff about fault management that I think I'm going to skip in the interest of time. I want to leave a lot of time for questions. So I want to close with a picture of the spacecraft that I have had throughout this talk. So this was a mission called LADEE. LADEE was a modest-sized lunar mission. Its job was to go to the moon, orbit the moon for 7 months, 8 months, I think, and do some explorations of the lunar atmosphere. It turns out the moon does have an atmosphere. It's just a very, very thin one, and there's not a lot in it. But enough about the science. We did some of this work that I described in conjunction with the LADEE mission, and we couldn't handle the entire model, but we got some good information from them about how large this technology would need to be in order to scale to LADEE. So LADEE had about 600 commands. It produced something like 25,000 pieces of data. The mission planning system on the ground data system mission planning system had 120-ish activities. And they tracked to 27 different state variables, propositions, and 21 different numerical resources. The planning technology that was used for LADEE was not PDDL, but it was sort of similar in spirit. It had roughly 12,000 lines of model code, and the flight software simulation for LADEE produced data at about 10 hertz. So even though all of these algorithms that I described for doing this validation are fairly fast, right? They're, for computer scientists, this is, it's polynomial time, it's boring. But the fact that you had to deal with the real data and the fact that you had to run all these abstractions means that this would be quite the chore. to be continuously running a piece of technology like the one I described in order to validate your model. So it's not like this is super simple, even though it's not, sort of AI complete. Okay, the takeaway. So model-based planning, as AI planning people think about it, is performed at a high level of abstraction compared to low-level system behavior for robots, spacecraft, and so on. You will have a simulator to use as an oracle. The flight software people need these simulators in order to validate all those command scripts that are part of the abstraction. To document those abstractions is to relate the planning model at that high level of abstraction to the low level of abstraction, both via the command abstractions and also via the function and predicate abstractions. Once you've done that, you can automate the detection of problems in your planning models. However, we don't quite know yet how to do much more than detect that the problems exist. I outlined a couple of ideas for what to do in order to fix those problems, but that's a challenge for the future. So I will close with this magnificent picture that was taken of the LADEE spacecraft. This picture was taken from New York City. The spacecraft launched from Wallops. Wallops Space Flight Center is in Maryland. It's not all that far away from New York. I wish I could, I can't remember the name of the photographer at the moment, but really magnificent picture. LADEE mission finished up about 10 years ago, so it's kind of nice to be able to do this and to pay homage to that mission and the work that we did using their stuff as an example. Okay, I think that's it. I will pause here for questions.
Thank you very much. Unfortunately, there is no applause on Zoom, but anyone with a question, you can unmute yourselves to ask, or you can type it in the chat, and I'm happy to ask it for you. Well, there is a way to applaud on Zoom. Eli is clapping now. There's a button. He says it's under the participant window. Oh, there we go. So I had one, I guess it's rather a straightforward question. So you mentioned when you were talking about animal and more expressive languages that there is a reason to use a simpler language. So given that we've been doing some exercises in PDDL, classical planning exercises in PDDL, perhaps you could explain a little bit what those reasons are.
Sure. I think it bluntly comes back to all models are wrong and some models are useful, right? Everything we do is a model of some form. Everything we do is some form of abstraction of quote unquote the real world. And so when you become an engineer, you become familiar with making these kinds of trade-offs where you say, well, sure, there's a better way to do this. It's more abstract, or it's more accurate, but it's going to cost me something. Is it going to cost me time? Is it going to cost me money? Is it going to cost me people? Do I have the expertise to do this quote unquote better? So it really boils down to a trade, right? You just have to say, hey, is this extra power worth it? And sometimes it's just not. When you look at a model the size of LADEE, where you say I've got hundreds of activities and hundreds of states and thousands of constraints and maybe thousands of activities, you might say, well, could I just model the low-level spacecraft directly using whatever my favorite representation is? And the short answer is maybe you could, but the model might just be too large. You might not be able to actually use it for mission planning at all. And if you can't, then you're going to simplify, right? And I think the same exact calculation goes for classical versus temporal planning. And it goes for temporal planning a la PDDL 2.1 versus something more sophisticated like XTAT or Animal, where you say, well, I may think that I need all of this power, but perhaps I don't. And if I don't, the ruthless drive to get the system fielded will cause you to use the solution that is just good enough and no better.
Jan Hao asked, is there any automated approach for predicate abstraction and command refinement?
Yeah, that's a good question. I think the short answer is no. And the reason why I think the answer is no is because if you look at the way that, so a lot of this basically is driven by the way that that lower level behavior works. That lower level behavior is a function of the interface, which, in Spacecraft is the flight software interface. And the people at mission planning don't get to dictate to flight software. Flight software dictates to everybody else. And by the same token for a robot, if the robot has certain behavioral primitives, then you are effectively building your planner around those primitives, whatever they may happen to be. And in order to automate the predicate abstractions and command refinements, I think you'd need much richer descriptions of what those interfaces and what those data items really are than people generally have. I'd love to imagine that there was a way to do this, but I don't see a good one. I feel like it's just going to be a manual process.
So Alison asked, how do you design which test plans to simulate?
Yeah, that's a great question too. So there are a couple of different ways to approach that. So the first thing that you could do is for every single action, you could simply say, hey, you know what? I have to design test plans that test every single action individually, right? And that's already going to be a lot of test plans, but you're going to get a huge amount out of that right away, right? It's sort of ablation testing on your actions. And it's a different way of thinking than traditional model-based planning, because you know that there's this adversary underneath you, which is the flight software and the command script level. And so it's not enough for you to just say, well, I want to make sure that the action executes when all its conditions are satisfied. You can't rule out that some other funny might occur. And so the generation of those test plans all by themselves is already difficult, right? You have to say, well, what extra propositions or what extra pieces of state could mess me up here? And it's also not the case that that only the action's going to work when all the conditions are satisfied. So, in the worst case, you basically say, well, I got to enumerate every combination of states, and that would be awful. But the other thing that you often find is on the fault management front, people are saying, we need to make sure that the fault protection system is going to catch faults when they occur. And so that all that sort of engineering testing that's getting done at the lower level of the system, all of that stuff motivates larger and larger suites of test plans that you can use on the planner.
So Ben has quite a long question. Do you want to ask it yourself, Ben, or shall I have a go?
Yeah, I can try. Hi, Jeremy. How you doing? Thanks for the great talk. So I was wondering, so through the process, I can imagine, and it's a little bit related to the last question, that you could have well-modeled parts for certain parts of the plan space, but unseen areas of the plan space. You might still have errors that you haven't seen yet. Do you think you could use the errors that you found before to detect possible errors in other unseen plan spaces? Or do you think that you'll just have to use the approach over many different plans?
Yeah, that's a good question. I feel like you should be able to do this, but I think it may be that what you're going to do is take advantage of, call it sort of partial insight into the plan space. So let's take our slew again. So if I find, well, let me make it concrete. So sometimes spacecraft are sort of longer on one body axis, and they're sort of short fat cylinders on another body axis. So imagine that the thing that I discover is that a slew that I plan with sort of a long rotation around the long body axis is prone to failure, right? Because, I don't know, my reaction wheels are under torqued or something like that. So that would be a nice sort of durable problematic action. And I would say, well, I don't care where I am. All I care about is that I'm doing a long rotation slew around the body axis. And I might say, oh, nope, I can't do that, right? I got to plan that differently. Whereas, shorter slews where, I'm sort of rotating, 10 degrees or 15 degrees, they always work. So I think of this sort of in the same way as I think of a tight constraint, a constraint on a pair of variables. It informs me about, it's very informative, right? Now, can you predict where you're going to encounter those long slews based on some initial state? Well, you can't, right? So that's about as good an answer I have to that question. It's a good question. I don't have a better answer than that.
Okay, thank you.
Is there a benchmark for these lower level systems? Yeah, no benchmarks like that exist, alas. This is the kind of thing that I think one could start looking at with, say, ROS-Plan and ROS, where you say, okay, so, if I have some robot and I've modeled my robot in ROS and I want to start doing this with ROS-Plan. ROS-Plan and ROS, I think, and whether it's in SRL or some other kind of lower level system, this is the kind of existing infrastructure that I think would provide a nice way to start exploring some of these ideas more. The challenge would be then that if I don't have a real robot and I don't have sort of real low-level robot behaviors and primitive scripts in SRL or even something that the SRL is going to toggle, you're not going to uncover some of the nastier stuff. You really want to be doing this on something as close to a real robot as you can find.
Yeah, I saw Ronan Braffman in the chat this morning, but I don't think he's here right now, who has some previous work on what's called performance level profiles, or PLPs, which is a way of specifying what are the assurances and conditions around a piece of software that need to then be translated into an abstraction. So a sort of standardized way of describing in PDDL terms the preconditions and effects of the action. And if he was here, I would have him give you a much better explanation of what that is than I can. But this sort of translation from the low level to your first layer of abstraction would be extremely useful to have for ROS in particular and robotics in general.
I don't feel like there's any particular barrier to describing the flight software or these lower level layers. It's just that people don't, or if they do, they don't do it with an eye towards establishing in a more automatic way this connection to the planning system. And it becomes plain to people for whom these planning systems are required that somebody's got to do that, but usually it falls on mission operations or the ground data system in order to do that work. And for a big mission, you can do that. For a smaller mission, sometimes it's just a lot more difficult.
So something that wasn't 100% clear to me was how can you tell if your abstraction is incorrect versus there's some variance in the world on which your flight software is operating, or are those just considered the same thing?
Yeah, some of the symptoms do look very similar to each other, and that makes it very hard to pinpoint which error you've experienced, right? So my favorite example is the one where you say, hey, I've screwed up the pointing error, right? So if I said, hey, I need tight pointing because I'm going to use my directional antenna as opposed to, the low gain Omni where I actually don't have to point at all. But, or if I make a mistake where I say, oops, I put a tight tolerance on a science target where all I need to do is point to the Earth. And so my pointing is all messed up. Well, what did I do? Did I give the wrong parameter in the command script? Or did I get the abstraction wrong? Or did I just write the model wrong in the first place? And you can see that it's quite hard to disentangle which of those three things it could be from the symptoms.
So Ben asks, do you think of this as a tool for human-in-the-loop planning? Could it be a way of actually fixing the detected errors? Or is it not even clear to experts where in the model the errors are actually caused?
Yeah, I think you can contrive examples that are hard, like the one that I described. And again, it's because the knowledge is captured in two different places, right? You know, I sort of purposely use this kind of cryptic representation for the data and the commanding, but that's often the way that these things look. Sometimes it's even worse, right? It's hex or some other, you know, even less comprehensible representation. So that's the key problem, is that, you know, it's these two very different forms of knowledge. They're owned by different people, and they are at these different levels of abstraction, and yet that the mission planning system depends on an understanding of what that lower level is in order to accurately reflect, or as accurately as required, reflect what the planning system is supposed to do. So I feel like for anything that's sizable and real, it's going to have to be at least partially manual. And so there is this big open question about, you know, just algorithmically speaking, what can you do? And then when you put this in the hands of people who have to design the planner, how much of that stuff actually ends up being useful to them versus the stuff that's just noise, or, you know, it's just not going to help them.
Okay, Yanni has a question as well. Have you and your team encountered situations where the errors you would use to fix your model were actually wrong and you ended up breaking the model?
Yeah, so let me just explain. This was work that was done about a decade ago, and unfortunately, right after we did the first sort of year and prototype of the work, we had to stop it, and so it hasn't persisted. But we do find, I think we find problems like the one that you described all the time, where you say, well, I don't quite know what's going wrong, and I'm sort of fumbling around trying to figure out how to fix it, and I break a bunch of stuff while I'm trying to fix it. And again, I'll just reemphasize that it's this air gap that you have between the true way that the lower system behaves, the lower level system behaves, who knows how it behaves, how do you find out from them what it's really supposed to do, versus you know, your understanding of it. And then once you've got it all sorted, what are you going to do about it?